Okay, we've got an interesting problem here today from the Berkeley Math Tournament 2024 Calculus number 6. We have the integral from 1 to 36 of the square root of 3 plus square root of x minus 2 dx. Okay, I thought it was pretty unusual having three roots in the same problem. One thing I want to notice on this, I did kind of change the problem a little bit. I changed this upper bound. They had something different going on where you had to solve for the bound. I just didn't feel like dealing with that part of it, so I kind of simplified it a little bit with the bound. Anyway, to get started with it, what I want to do is I want to try to clean up this whole thing with a u substitution. It's hard to deal with it with all the nested square roots, so what I'm going to do is just set u equal to that whole thing there, which is going to be square root 3 plus square root of x minus 2. The reason I want to do this is because then all this is going to become just u to the 1/2. And then at that point, hopefully we've got something pretty simple to deal with that we can do like power rule on. Now for the derivative, I don't really feel like taking the derivative on this and getting a du. So instead, let's solve for x on this. What I can do is bring the 2 on the other side. So adding 2 on both sides, we get an equation u plus 2 equals this thing. And then square both sides. So squaring out this, u squared plus 4u plus 4 equals, when we square this, 3 plus square root x. Technically we should have absolute value, but this thing's always positive, and not that it really matters, but the bounds are always positive too. So then I'll subtract 3 on both sides. If we do it here, that goes away, and this is going to become just a plus 1. Not really sure why I need to change colors, but anyway, we'll square both sides to get our x. So we're going to have x. Square this whole thing out. This is kind of tedious, so this is going to become some big long expression here. Multiplying it out in columns like this makes it easy for me to add it up afterward because we've got all the like terms in columns. So we do that, and we're going to have this big thing here. And so this is going to be just our x value. And so next we'll take our derivative to get a dx value up here. So this is going to be just power rule differentiation. So 4u cubed, 24u squared, 36u plus 8 du. Okay, so now we can go ahead and substitute. You'll notice 36 and 1 for these bounds. Both of those are perfect squares, which is good because we're plugging in to a square root right here. So when we do this, you plug 36 in here. Square root of 36 is 6, plus 3 is 9, square root of 9 is 3, minus 2, and this is a 1. Plug 1 in here, you end up with 1 plus 3, square root of 4 is 2, minus 2, this becomes 0. Then, like I said before, this whole thing here is going to become u to the 1/2, and dx is all this. And then from here, let's distribute the u to the 1/2 into all the terms. And now what we're left with is just going to be power rule on each of these terms. And now at this point, I'm getting concerned that I might be getting an ugly fraction out of this. But anyway, I hope the answer is 2024, but I'm not sure. Now evaluating at 0, because we've got u and everything, clearly the 0 is just going to be 0, so we're not worried about that. You plug 1 in, that's going to be nice because it doesn't matter that we've got 7/2, 5/2. Each of these terms is just going to be a 1. So all I need to do is simplify this giant fraction, or all these fractions. We're going to have this 8/9, 48 over 7. Oh, this is terrible, right? 72 over 5, 16 over 3. What can I do? I guess with these two, we can get a common denominator of 9. So this is going to be 48 plus 8, or 56 over 9. But from here, I'll spare you the trouble of getting a common denominator. And so for my final solution of this, we get just 86/56 over 15, and that's it. For a second, I wanted to pretend that maybe 2024 times 4 was 86/56, but it's just not true. I think the lesson here is when I messed with the problem, I really made it quite a bit worse, or I made it uglier. Maybe I should have just stayed with their version of it where you have to solve for the upper bound. I didn't really want to explain that either, so I don't know. But anyway, hope I didn't make a mistake somewhere, because it's going to be embarrassing if that's not really the answer. Okay, that's it for today. Thanks everyone for watching. Have a good day.